Okay, good afternoon, everyone. My name is Carlos Lizárraga, and today we are continuing with multimodal large language models using Hugging Face transformers. And this session will be run between Enrique Noriega and me. Okay, so I'm gonna share the link in the chat. So everyone can follow. Okay. So let's start. And if you have any questions, please open your mic or just write the question in the chat and we will be taking care of your questions. So on the past 2 weeks, we have been talking about Hugging Face transformers and how now everyone is more easy to use all the large language models that are sitting in Hugging Face, and then in order to do our tasks, different tasks. The first session 2 weeks ago was about text, analyzing text using NLP transformers. Last week we saw computer vision transformers to analyze different images. And today we are going to be handling what is called multimodal. So multimodal, it's a combination of text, video, and sound. So you will find an introduction to these large language multimodal models. And these models are used for image captioning or visual question answering, text-to-image generation, speak-to-text and text-to-speech tasks, also audiovisual analysis, and when you have different modes, cross-modal retrieval, and also we can do some multimodal sentiment analysis. We will be showing a Jupyter Notebook at the end of the second part of this session to show some examples how to use these models from Hugging Face. Okay, so there's a presentation. We're going to follow this presentation. Okay, so lately, basically, many people are using multimodal LLMs because now they have augmented the capacity of these models to analyze different types of data. And this data can be, like I said, text, images, and video and audio. And also these models, they can understand complex ideas, and also they can create new uses for searches, image searches, and also it makes easier to for us to interact with the computers. There are some challenges and opportunities in these multimodal models. And one of the challenges is that we need a large amount of quality data to train the models. And sometimes this data is not available. And also this data can be biased. So the models will inherit all the biases from the data. And also these models can present different opportunities to be applied in different fields like healthcare, education, and also teach us how to improve our teamwork between people and machines, and also to let us to make new discoveries in research. Now, if you look at this image, it says, congratulations, you're now the branch manager. Is this, how do you read this this phrase? Is it irony? Is it sarcasm? Is it cynicism? What do you think? Large language models have some difficulty sometimes to understand additional features from the data we are inputting. So these models need still some improvement, and at some point, these models will always be confronted with hard challenges. Like, for example, in the next slide, hello? The next slide, I'm just showing different types of information. The data can be complex. So even for us, sometimes it's difficult to understand exactly every piece of information that appears in these documents. And we expect, or we're trying that our models also can handle this type of information and extract all the important information from them. So let's see. Okay, so we need to understand how multimodal large language models work. As we mentioned, when we're talking about modality, we talk about text, image, and audio. And also the tasks these multimodal large language models can do is like image captioning. When they generate a description of an image, we can ask questions. So visual question answering, we can answer questions about some image. Also, it will try to understand some video, and it will try to extract the content, the type of action, objects, and events. And also it can create images based on a textual description. Or if you are building like a audiovisual item, like a movie, then you have to align audio and visual information in the videos or movies. So it requires a lot of synchronization and different modules to coordinate in order to produce the tasks that we are having our system. So this is a very general description of the architecture of the multimodal large language models. So on the left, we have the input data, can be an image, can be a video, can be an audio segment file. And depending on the mode of this data, then the image video can be processed by different encoders. So we have all these different types of encoders to process the image video. If we have audio, then we have a different set of encoders that can process the audio. And also, then we can have additional things. Then the output from the encoder goes as a text, and it can be handled by different types of models, like multi-layer perceptron, or the linear projector, or cross attention, etc. And then this is sent for the large language models to process. And then these large language models will have some output. It will send to a tiny transformer, and then that will be transformed or generated into the output. Can be an image, can be a video or audio. And if it's an image, maybe we're using stable diffusion, or if it's video, we're using stereoscope, or if it's audio, we use the audio LDM. And so we have this output. As this is the part of the multimodal generation. And the whole process is try to understand the input and generate the required output. Now, this is an ideal to have some type of transformer that we can have all these different types of inputs. Can be text, can be an audio segment of audio, can be an image, can be an infrared image from some sensor, can be a point cloud coming out from LiDAR, for example, can be a video, can be an X-ray, can be a table, can be this motion data from sensors. It can be a time series coming out from a sensor, or for example, a weather station. Can be hyperspectrum, for example, data coming from our satellites. Can be a graph, and any type of data can be input to these sequence tokenizers, and it will process it. And then, depending on what is the context, the output can be like a stock analysis, stock market analysis, can be a RGB image item, can do a graph analysis, can be a weather forecasting, can be the autonomous driving vehicles, can be the information from an infrared camera, remote sensing, recognizing activity, speech recognition, medical diagnosis, like a 3D recognition, or understanding some text. So this is the ideal thing that we are looking for. And eventually we have some models that do something of this, like this, but still there needs a lot of work to be done. Okay. So these are the processes. Depending if we're doing a text like natural language, or you're doing an image, or just a point cloud, like a three-dimensional image, or an audio spectrum. And this will be sent to these tokenizers. And these data to sequence tokenizers will split the information in different tokens, and that will be analyzed by the multimodal model. We can change some parameters, we can adjust some parameters over here, but we can't change these parameters over there. And then the output can be a paraphrase, can be a sentiment, can be an inference, can do a classification, can be a detection, a segmentation, or another classification for the point cloud, can be segmenting some parts of the point cloud, can do a scene segmentation, and in the case of the audio spectrogram, can do speech classification of the input. So it's a complex task because we have to involve several layers and several modules before getting some answer back. Okay. Now, how do these models understand the information we give them, and depending on also on the type of information we are handling? And these models have employed two main strategies that integrates the information. So it can do an early fusion, meaning that all the information that you give to the model is going to be pre-processed before getting some answer, or it will process each element, and then after it has processed each element, combine them into a late fusion. And for example, if you're asking your model to give you an image of a person skiing on a slope that is surrounded by forests, then the model has to analyze the person, the action of skiing, a slope mountain, and also the forest, and then at the end can combine to produce a single image. So that's can be an early fusion or a late fusion. And in this process, you can have an encoder. The encoder can handle like a single stream or multi-stream, and then you can do a cross interaction between the different tasks. And also you can do a joint interaction, or you can have encoder, decoder, like these models over here that can do encoder, decoder, different tasks and different models. So it's not a simple model. Okay, there are some popular large language models which are multimodal. There's the CLIP, which is contrastive language image pre-training. And this model handles text and images. and classifies images or creates captions from the text. Also, DALL-E 2 from OpenAI also is a generative model for creating images which are very photorealistic or of some art, just following the natural language description. Also from Google, we have Palm, which is a multimodal extension of the Palm language model, and also generates image from text prompts. And it's developed by Google. And also we have the Vision Transformer from Google, also to create images or state-of-the-art images. Also, we have the Vision Language BERT, which is a multimodal transformer. And it also has an architecture similar to what BERT has. And lastly, we have the model from Facebook AI, Align, that can translate text to images and vice versa. So there are more than these models, but these are the most popular ones. And if you try to follow up what's new on the horizon, this is how the multimodal large language models have evolved in the last 2 years. So every day you will find a new model that has different characteristics, and you will see that there are not many companies who create these multimodal large language models. Usually those are large companies like Microsoft, Google, Meta, Amazon, and so on. So it's not something that you can do on your garage. All right. Because trying to create this type of models, you need to have the necessary or the required hardware, and that amounts to having multiple farms of GPUs, and that will be expensive. Okay. So what are the benefits of using multimodal? So the multimodal can improve the tasks by combining different types of information. It can improve how we interact with computers, and also these models can create unique content. So we can do many tasks, and these type of tasks are very productive. These models have some challenges. Like I mentioned before, you can have data scarcity and bias. For example, you will find a lot of conversations about how the large companies are training their models, where they are acquiring all the data, and if the data is open or if the data is private, and if they are challenging like copyright laws, using information without the author's consent, etc. So those are some of the challenges. Also, the alignment between the modality and fusion. So you have different types of modalities, and these models are trying to combine each part before they try to get the results. And also, these models are just like black boxes, so sometimes it's difficult to interpret or explain the outcomes, because we don't know exactly how the models will process the information. What we need to understand how multimodal languages work, well, we need some basic knowledge about natural language processing that understands human language, also computer vision, so how computer vision works, how the computers handle all the different images. And also we need some basic concepts about machine learning and deep learning, and how these models are trained on large data sets, and they must have some attention mechanisms and transformers to combine all the informations to process the different types of data. Okay. On talking about the general architecture of these multimodal large language models, so how can we extract meaningful representation from each modality? So we need text encoders. They will process the textual data. We need image encoders to extract the visual feature from images. And also we need audio encoders to process audio data using different techniques like doing spectra from the sound signals, and also using different neural networks in each case. And this is an overview how do these large language models work. So we need different encoders for images, for audio, for video, and then the output from these encoders go to the large language model that will try to create the instructions for the second part. If we're going to create an image, so we have an image diffusion model. If we're going to produce some audio, we need to have some audio diffusion model. And if we're going to create some video, we need some video diffusion model to create the output. And so it's not a single task or just it's going to be a full set of different mechanisms. Okay. What about the fusion mechanism? When the systems are preparing the output, the models will have to fuse or make a fusion of the different elements. For example, it's going to create an image of a person skiing on a slope of a mountain inside of a forest. Then you can combine the different representations at an early stage, and then at the later stage do the fusion, or you can try to make a previous fusion from the beginning, or you can do a joint embedding, or you can involve attention-based mechanisms that can understand the different importance of each modality based on the relevance for the tasks. Like, for example, in this case, the description is the vibrant plumage of a parrot perched atop a sleek silver laptop contrasts starkly with the deep green leaves fluttering in the background. So it's combining different images. You have a parrot, you have the background, you have the laptop, and also you have the parrot standing on the laptop, and has some contrast with the background. So this is all the different mechanisms you have to involve. You have to decode each layer, and then all the different, you have to involve different vision encoders, and then at the end combine the different information to create a fusion layer and produce the output. Okay. I know this is a very hand wave explanation how these large language models, multimodals work, but well, we're still black boxes. And then the output layers, once they have the different products, they will try to classify, or they may generate an image, or they can have a sequence-to-sequence tasks like machine translation or answering questions about an image, for example. We will see some of examples that we can see exactly what I mean by that. This is another example of a pipeline for image comprehension and generation. So the question is, this seal is adorable. Could you change the pose for him? So this is the question. The question will be analyzed by a text tokenizer, and you have the image. The image will be analyzed by the image tokenizer, and then the image tokenizer will use different encoders to try to produce it's going to try to change a pose for the seal. So we will use different layers and transformers to produce the output. And then the output from the image and text tokenizers will go into the large language model. And the large language model can be any of these type of models. And then they will try to produce the output. So on the text tokenizer will answer, yes, there's another pose. And also the image, the tokenizer will produce the seal in a different position. And this is how the different layers and different transformers and neural networks are involved in order to produce the output, the image output. Okay. Okay, so the idea of this session is try to use Hugging Face resources in order to produce this type of tasks. And we know some of the benefits of using Hugging Face. We have seen this type of benefits for the last 2 weeks. So there's a diverse model selection. They are user-friendly interface. They are adaptable. There is a large community that can give us support, tutorials, and also everything can be seamless, integrated into an application. And basically, we can use any of the frameworks like TensorFlow or PyTorch to produce these results. If you visit Hugging Face, you will find that there's a large number of models. For example, for image text-to-text, there's about 590 models. For visual question answering, there's 382. I counted last night. Document question answering, 193 models. Video text-to-text, 18 models. And any-to-any mode, about 775 models. Okay, so the next part of the session will be in charge of Enrique, and he will be explaining Jupyter Notebook. They will find in the notes for this session, and he will review several examples of multimodal large language models, different cases of image question answering, diffusion models, automatic speech recognition, and text-to-speech examples. Okay, so let's just stop this. Okay, escape and go back. Okay.
Hey there, Carlos. Thank you so much for this great explainer. Can everybody hear me okay and see my screen?
Yes.
Perfect. So I'm Enrique. I'm going to show you now a Jupyter Notebook that we're going to be running on Google Cloud with several of the examples of multimodal transformer models that we can find on Hugging Face. The purpose of this is to show you how you can relatively easily leverage Hugging Face to power your own applications using some of the methods that were just described and explained by Carlos. This notebook, you can find it on our GitHub page. So it is public. You can download it and you can adjust it to your own needs. The only prerequisites is that if you try to run it yourself, you will have to download the data files that we also have on our GitHub repo and manually put them on the workbench of Google Cloud. So the first thing that we got to do is that we need to install our required libraries. The main one is going to be transformers because that's the backbone of Hugging Face, the models. But we're also, since we're doing multimodals, we also need diffusers. We also need data sets with the optional audio component, and we need the text-to-speech library. You don't really need to worry too much about the other ones. They are just requirements. So classically or typically you use pip So pip install this, and it's gonna take a little bit, but once it's done, we'll, excuse me, we will be able to run our examples. And as far as the data, we have one image that we're gonna make use of, and we have a few sample audio files that we're gonna use to showcase how we can do the multimodal. Feel free to interrupt me for questions if there's something that is not clear. And I think that we're almost done installing the dependencies. Usually it takes a little bit of time. Something else to note is that given the size of these models, you want to have a GPU. The reason for this is that it is really slow if you have a CPU-only computer. Colab allows us to use the NVIDIA T4 GPU, but you could use Cybers or you could use the HPC. Okay, so we're gonna ignore some of the warnings because they're not really relevant for this demonstration. But as Carlos was mentioning, multimodal models are just models that may take different types of inputs and outputs. That means audio, text, video, and pictures. It doesn't really matter the order. It could be you could have one modality at the input, another at the output, or multiple at each endpoint. First, we're gonna focus on one of my favorites, because image question answering. I like this because it is pretty astonishing how you can just give a picture to a computer and just have it tell you something about it, as if you were speaking to somebody else who's staring at that picture. Since we're using Hugging Face, the first thing that you gotta do is that you need to identify a model that is fine-tuned for image question answering. I identified this one, and this is a good example of a specialized model that somebody fine-tuned. I do not know who is the individual or group behind this, but it works really well. And they have multiple revisions. So the one that we're going to be using today is fairly new. It has almost 1 month of age. So we need to set the model name and the revision. That's the index that we have for the Hugging Face hub. If you were here on previous sessions, you might remember that each model is usually paired in tandem with a tokenizer, and we fetch that also by the same model name. The first thing that we need to do is actually pull the model down from the hub, and we're going to make use of the auto classes for that. So that is that, because sometimes you have different architectures. Instead of having to know explicitly what is the name of the architecture and the class that implements that neural network architecture, the configuration helps the auto class to load it dynamically. What we're going to do here, what we're doing in the cell, is that since this is a type of a causal language modeling task, meaning that you give a prompt and then it's going to complete it, and it's fine-tuned to answer the question from the input prompt alongside the image. This is we are using the auto model for causal LM, and the auto tokenizer is just the default class that you use to load that companion tokenizer. Takes a little bit, but so the model comes in, the actual data of the model comes in the safe tensor files, so you can see that it is 3.74 gigs. Since we're running in the cloud, it doesn't really matter if how big it is, because it can be downloaded fairly quickly. The next step is that since we're using GPU, we're going to send it to the GPU. When you're using Hugging Face or PyTorch, you usually use a method called to, and you send it to the device, the accelerator device that you want to use. T4 is an NVIDIA GPU, so we're going to use CUDA. CUDA is just the marketing term that they use for their GPU runtime framework. So if we go here to T4, we can see that looking at the metrics of the performance, at some point we loaded into RAM the model, and you can see this spike here, but then we mapped it to the GPU, and that you can see that the memory is now half filled on the GPU, and the system RAM decreased. That is a result of calling model 2. That being said, we have the model ready, so let's do something with it. The first thing that I want to try is that I want to load a test image. So here in the notebook, on the workspace, I uploaded the test JPEG, and we can actually visualize it. So let's wait for it to finish thinking. Yeah, there you go. So what is this? This is actually, like, fun fact that I generated this image from Meta AI. But you can see it, right? It's a kid eating a salad and drinking a glass of water. So let's actually do some question answering about it. Since we have an image, which is a JPEG file, we need to pre-process it. This model, being a visual question answering model, has a special method called encode image. So we're going to run it on the image object that we loaded, and we're going to see what's the result. Here we can see that it's a tensor and that it's mapped to the GPU device. And what you see here are the numbers. It's the vector representation of this specific image. We're not talking about RGB pixels anymore. We're talking of a tensor on a specific vector space. And if you're curious about how big it is, you can always use the size method on a PyTorch tensor. The first dimension is the batch size. This is a single image, so the batch contains just one object. But then we have 729 different vectors of about 2,000 float point numbers each. So you can think about this as a matrix, but instead of RGB colors, it represents something on the same space as the model. So that's half of the question. So we already encoded the image, but now let's actually ask something about it. So the first question is going to be, what is the color of the eyes of this individual? And I just want to scroll up a little bit such that if you didn't pay attention to the detail, you can see here. So I see them green. So let's see, what does the model think about it? We're going to define the question as a prompt in the string, and we're going to answer the question. The arguments to answer the question is the encoded image, it is the actual prompt, and it is the tokenizer. Just remember that the tokenizer was downloaded previously at the time of loading the model. The output of this is that the individual has green eyes. So I'm glad that I got it right, and I don't have any sort of confusion of what was that color. But like, that is sort of like pretty trivial. What if we like ask something a little bit more complex? So what is the boy eating and drinking? So now we're asking about two different things at the same time. The boy is eating a salad and is drinking water, red. And if we take a step up and ask something a little bit more abstract, what is the overall color of this picture? So what is the tone or the hue that the model thinks is being represented? The picture is predominantly green with some accents of blue and yellow. So let's just scroll up a little bit more. And I guess so. So you can see that the background has like a shade of dark green. There's an apron that is also green. This being a salad contains lots of greens, green eyes, and so forth. But also the shirt of this kid is yellowish. There are some Roma tomatoes, I think, here that are kind of more on the color spectrum of red, yellowish. We have the croutons and so forth. So I guess that this is pretty accurate. So the key insight here is that when we are asking a question to a multimodal transformer, we are passing a text prompt and an image encoded on the same vector space, and we can ask whatever we want to know. So you could ask the model to describe the scene. You could ask to count how many elements you see there. I'm not saying that it's going to be right, the response is going to be right, but it's going to elicit a response, taking as input multiple modalities. But this was going from image and text at the beginning to text response. So what if we like flip the script a little bit and speak about the diffusion models? So diffusions, if you are familiar with DALL-E, like Carlos was mentioning, or if you've used Midjourney to generate images, those are diffusion models. So diffusion models take a prompt in which you describe a scene, and then they synthesize an image that represents that description. So the way they work is that they take the input prompt and encode it using a contrastive class of transformers such as clip embeddings and generate a vector representation for that prompt. That is encoding the prompt, so going from text to an intermediate representation. And then they decode the prompt into an image, a noisy image that we don't actually see. So that's the decoding step, an encoder and a decoder. Once we have a decoded noisy image, they apply a diffusion procedure. A diffusion procedure is an iterative, if I had to summarize it, I could say that it's a loop in which at each step, another model is going to try to remove the noise from that generated image and make it more close to what would be a truly drawn or pictured image. So what we did here is that, again, using Hugging Face, we're going to make use of the diffusion pipeline. So we are going to use a stable diffusion provided model, and we're going to send it to the GPU as well. Once it's, I mean, you can see, actually, you can see, yeah, that there's a clip feature extractor that is the encoder that I was mentioning, and there are a bunch of different layers to our neural network. But using Hugging Face and pipelines, it is really easy to generate the images. So the input is going to be text. What if I want to see a cat eating a bag of chips? I can fetch the image, and you can see how there are 50 steps here. This is the diffusion procedure. You can make the image more accurate or more realistic with more steps, but the trade-off that you pay is that you spend more time running the model. And yeah, I could say that this looks pretty accurate from what I asked. So, but let's try it again. It's gonna take some steps. It's pretty similar, but you can see that it's not identical. And this is a property of the probabilistic nature of the model. We could set a seed always to the same one and probably will get the same answer. But this is not the only thing. What if I want to see a young couple playing pickleball? Yeah, so what I want to say about this is that overall, yes, it looks accurate, but you can see that there are some artifacts of the diffusion procedure. Like you can see that the faces are like a little bit strange. There are some weird things like the hands are sort of merged with the I don't know what's the name of this bracket or something. But it is kind of weird, but it is sort of accurate. So the reason for this is that we are running an open source model on a small GPU with a limited number of diffusion steps. The image generation landscape has been advancing very quickly at a brisk pace. And usually if you want to create those hyper realistic images, you need to load this into a GPU that has 40 gigs of RAM or 80 gigs of RAM, and it's going to take much longer to do so. It requires a lot of hardware. So usually you use a cloud provider for that. It could be Meta AI or OpenAI, whatever else. But the point here is just to give the demonstration. And what you ask for, it doesn't necessarily need to be something realistic. So how about a turtle riding a bicycle? I could draw it, or I can visualize in my mind here this, but let's see what we see, what we get. So I'm just opening chat. You're using Google Pro, but what service would I recommend for higher computation? I could probably use a I could probably like if you want to do it professionally or for profit, use AWS and deploy your own virtual machine that has the notebooks that you want to run or the Python scripts that you want to run. So yes, turtle riding bicycle in a cartoonish style. Let's see what happens. I haven't run this yet. And yes, the more steps that you add, the image is going to be less noisy. That depends on like more similar to what like, that's relative, but it's going to be less noisy. Of course, you're limited to the capabilities of the model that you love. Yes, so if you set the seed, you should get the same thing always. Okay, so here, like we get the turtle running a bicycle with a cartoonish style. I think that this is better than realistic. So the key aspect here is that you can, on the prompt, you have plenty of leeway on defining what you want to do. The more explicit you are with the prompt, the better results you're going to get. If you use a service like Midjourney, they're actually going to map your prompt into something more explicit to get better results for you. So that's it for multimodal text and images. Multimodal also means that you could get you could use audio speech, and let's try something like that. First, I don't know if you can actually listen to this. So we're gonna use a sample file that I got from Harvard and see if you can listen to it through Zoom.
No. We cannot hear.
You cannot hear? Okay.
No, because it's a session.
Let me see. Well, on the interest of time, let's see the transcription. What we're going to do is that we're going to use Whisper. Whisper takes an input audio file and generates the text out of it. So you can hear it, but now you're going to be able to read it. And you will have to take my word and trust me if I tell you that the transcription is accurate. But then offline, you can download the file and verify it yourself. Let me see if I can change from my headphones to the speaker. Okay, so we loaded the Whisper model. Let's run Harvard Web. Yes, stale smell of old beer lingers. That is right. It takes heat to bring out the odor. Olive restores health and zest. Salt pickle tastes fine with ham. Tacos al pastor are my favorite. Successful food is a hot cross bun. So I'm going to try to play it again. Please, Carlos, can you tell me if you can hear this? Oh.
No, it has to do with how you set up your Zoom.
Oh, okay. Well, sorry about that. Yeah. Okay. So with Twister, this is a tongue twister that I recorded. Oh, I think, yeah, hold on. Can you hear that?
Nope.
Okay.
Someone said you can reshare your screen with audio.
Let me try that. Share screen, and computer audio. Yes.
Let's try again. No.
Okay. So yeah, fortunately, what we have here is an almost perfect transcription, but I said Peter Piper, not Peter Piper, because that's my non-native English speaker accent that is not picked up correctly. But then you could also do text-to-speech, which is the other way around. For this, we're going to use Cocky. Cocky, it's a Hugging Face.
Did you skip some previous cells?
Maybe. Let me try it again. See if
No.
okay. Well, I'm gonna give you. We're almost out of time, so I'm gonna explain you what TTS means. That is text to speech. In text to speech, you give a an input text prompt and get an output audio prompt. So when you run this notebook, you will use a sample. This sample is my voice. So I recorded myself with microphone, and then I can use this TTS API or this transformer model to generate a wave file that speaks out what I'm adding as a prompt. So in here, I'm saying this is voice cloning, and I'm setting the language to English. So this could generate a wave file if when I am able to fix this cell. But something else that you can do is that you can ask for another language. So this is the same input, but in French, spoken with a French accent. And then you can clone your voice and actually speaking languages that you don't actually really know how to speak. So this is Portuguese with Brazilian accent, and it's the same. This is voice cloning, and you can actually do multi languages with different voices. So here's an example of when you run it, how you can use a tongue twister or speak a tongue twister in Spanish and display it. So I think that we're at time. Let me see if you have any further questions. I apologize for the TTS. I swear that it ran when I tested it this morning. But yeah, so this is one flavor of what you can do with multimodal models with Hugging Face, and there's a lot more stuff that you can do. So this is just a brief survey, but in reality, there's always more stuff coming out, and like you're going to see on some of the later sessions that we do, that you can actually do this with Gemini, or you can do it with GPT as well. There are some open source LLMs like Lava. This is not LLM. This is specific language models and transformer models on Hugging Face. But in reality, the line has been becoming more blurry between the capabilities of models now that we're on the age of LLMs. So yeah, that's it for the demonstration. And I'm gonna stop sharing my screen. And yeah, Namik.
Yeah, Namik here. Thank you so much for a great presentation and all these materials. They're really great. And then I had a question about the Hugging Face compared to using OpenAI API. So let's say I want to develop an application and for certain purposes. So would you like compare like what's the advantages and disadvantages of using Hugging Face models versus OpenAI API?
Yes. So with OpenAI API, you're going to get probably better quality results, and it's going to be easier for you as a developer to do it. But this comes at a cost, so you need to pay for their services. You should, and like if you're building an application, you might be able to afford it. It depends on what are your requirements. Some other concern that you may have is privacy. Like all the data that you do is computed on back end of that cloud provider. In this case, OpenAI. But maybe you're using you can actually run GPT on Azure. That travels to their data center, and this is the same for Google or for whoever, like Midjourney, whoever. If you want to use a Hugging Face model, usually you run it on your own device, so that means that you need to have at least a computer that has a GPU with enough memory to load that model and run it. Depending on the model that you use, your mileage may vary about the quality of the output. Nowadays, like things are tending to converge to LLMs because just by their sheer size, they give you better quality, but then you need to pay the price of hardware or provider to run. So I mean, if you're playing around or if you have very specific needs, you could use Hugging Face. But if like you have budget and you want the best quality, you might want to go with a proprietary provider.
Thank you so much.
Mm-hmm.
Okay.
Well, thank you everybody. So using Hugging Face models, can you tweak them, or they're always pre-trained? Yes, you can tweak them. You would need your own training data for the specific task that you want. And you need to know how to pre-train them. So just a self marketing here. We're going to start a new workshop in 2 weeks called AI Hacky Hour. We're going to explore how to fine-tune models using Hugging Face. Stay tuned for the details.